Hello guys, good evening. So this is just a follow-up video for the gradient descent blog that I recently wrote. And in this video, I'm trying to, show some how the gradient descent works in, by using some numbers so that we'll get much more intuition behind these things. So let's just get started with the basics. So I hope you already know a little bit of theory about the gradient descent, and I highly suggest having a little bit background on the theory of how gradient descent works before jumping into this video. Otherwise, you'll be totally lost in this video. So let's first start with that HX right over here, which is our hypothesis, hypothesis for a linear regression, or you can say multiple linear regression, theta naught, x naught. So x naught, you might see that, you'll see beta 1, beta 2, something in a statistics. So they are the same thing. The one unique thing is x naught, but in gradient descent, we assume x naught equals to 1 because it's going to help us to put that in a metric notation. That's the one and only touch, or one and only region, I would say. But x naught equals to 1, which means it's not going to change the underlying assumption or underlying thing, which is same as our statistics beta 1 and beta naught. Okay, so in the gradient descent, the thetas are randomly generated. And I'm going to do the same thing. Let me assign a random number, 0.2, 0.1, and let's do 0.5. So I just randomly chose those numbers. And these are my x variable, meaning these are two variables, and this is my target variable. So this is multiple linear regression. And one of the most important thing in gradient descent algorithm is feature scalings. The variable has to be scaled, in a same unit. Either it can be min max scale or standardized scale, because otherwise if the features are not scaled, the gradient descent wouldn't converge, or it will take a longer time to convert. So it's always very, very good decision, or you must, in other words, you must scale your features to get the efficient results. Now, these are my features, values, features, which I randomly generated. Okay. Now, what does HX means is I'm predicting the value, by using the thetas and x, I'm predicting the values. So let's do the same thing. Let's predict the values, with our initially randomly generated thetas. So as the formula says, theta naught, I'm going to do f naught. I've got to reference that thing. Multiplying x naught is 1, which we already says in the gradient descent. Then theta 1 f4 into x1, plus theta 2, do f4, doing absolute reference in Excel, x2, and pressing enter. So that's my predicted value. Copy it down. So this is my ground truth. This is my predicted truth. That's the thing. Now, the other thing that you can see is MSE, which is our error matrix, or you can say a formula that helps us to calculate or figure out how much error we have made while predicting our values, how far we are from our ground truth. And our goal is to minimize this error using any kind of algorithm or optimization algorithm like gradient descent. So let's calculate how much error we have made. So MSE means mean squared error. As you can figure out from the definition itself, you gotta take mean of the squared error. So let's just find the error. So error is x minus y, and it says mean squared error. So I'm gonna first of all square this one. So this just gonna give me squared error. I'm gonna copy it down. Then to find the mean, what I'm gonna do is equals to average this thing. Yeah, this summation thing is the same thing. What does summation mean? It's just summing all of those values from I equals to 1 to m, meaning like all of those rows, I'm summing all of the error of those squared residuals. And then what I'm doing, divide by m, means I'm dividing by how many numbers or how many number of rows are there, which is in other words, which is saying take the average, so that's the same thing. Now this is our what do we say, mean square error, and I'm going to copy this and I'm going to paste it here because I'm going to need that later on for other purpose. Now that's not actually how gradient descent works. Gradient descent works by updating the theta in such a way so that we'll have a minimum MSE, after a certain iteration of maybe 100, 200, or 300, depending upon the problem. After certain iterations, we'll have the minimum mean square error or minimum error in general. So for that, our formula is here. You can see that big formula, but it just looks big, but it's just simple. Let's just look at that part inside the parentheses. So you can see I equals to 1 summation m h naught xi, which means predicted value minus my ground truth, then multiplying by that respective x value, and then what I'm doing, I'm taking sum of all of those things, then I'm dividing it by m. So in other words, what is asking us is to, again, do the same kind of average kind of thing. So let first of all calculate the sum of these inside values. So it says h naught xi, which practically means, what value you will get, or what value you will get whenever you predict this thing, x1 and x naught 1, meaning first row of x1 and first row of x2. So in a similar way, I'm calculating, in other words, is asking us to find the hx of that one. But I'm also, what I'm going to do, hx, and then I'm going to do minus y, and I'm going to put this in a parenthesis, and I'm going to multiply it by 1 because we know that x not equals to 1. That's what we assumed in a gradient descent. Let me put that enter, and I'm going to pull it down. Okay, that's what I have got. On here, we're going to do the same. Let me put this in a parenthesis. Hx minus y multiplied by x1, this time x1, not x naught. Okay, so x1, and then I'm going to put enter, and I'm going to pull it down. Okay, and same I'm going to do for the x2 also. So hx minus y multiply by x2, enter. Now this is not the whole value. This is just, we just calculated the each error, but what we actually need is we need to sum those error and divide by m, meaning, like, for example, you have a m number of apples, and somebody told you sum those m number of apples and divide it by m. Does that sound familiar to you? For me, it does, because it sounds like he's actually asking me to take the average, and it's the same way what it is doing here, sum those error, sum those whatever this inside value is, then divide by m, meaning average, take the average of all of these things. And here, that's the same thing I'm going to do. I'm going to average all of these things. I'm going to copy it down to here, and I'm going to get that values. Okay. Now, this is not what my new theta values are. This is just the inside portion, this between this parentheses. So what my theta not gonna be whenever I make that update is I have to use all this formula. So theta naught is here, minus my alpha is, let me put this in F4. My alpha is 0.1, and this is a hyperparameter, and I randomly choose this value. Okay, so let me put this F4 in here, this one F4, multiplying by our parenthesis inside value for theta, the theta naught, which is for us is this one, and I'm also going to put this absolute reference. That's our new theta naught. Let's do the same thing for theta 1, which is theta 1. I'm going to put this in a minus learning rate into for x1. Okay, and I'm going to do F4. this one. Then I'm going to do here again for theta 2, I'm going to do theta 2 F4 minus, the alpha, which is learning rate, F4 multiplied by that inside value. And I'm going to do F4 and put it print. So now I'm just going to copy this at the moment. I'm just going to copy this here and just put it here as an option. So what does this thing, as you can see, these thetas and these thetas are different, means our theta is updated. After that one iteration, our theta is updated. Now let's update, meaning let's use this new theta, because these things will go on and on until we reach some convergence, or until we reach that, like for example, we set our iteration for 200, so until it reaches that 200, it's gonna, go on in this loop on and on. So let's just update this value. So I'm going to do Control C here, and I'm going to update theta naught with that new value. Control C, and you can see there is something changing, or most of the things are changing in the background, which I needed. So as you can see, again, our theta is updated to a new value. But look at the MSE. That's what I want you to focus on. This MSE, you remember I copied it whenever it was the first theta's values, whenever we randomly selected, it was 0.333, yeah, on iter 1. So MSE, let me do iter 1, I have that value. But if I list in this was on iteration 2, you can see my MSE is decreased. And I think that's what gradient descent does, that's what my goal is. My goal is to decrease my mean squared error. Now let's do one more time, let's go to the third iteration, So I have this updated theta 1, and I'm going to copy this, and I'm going to paste it here, and I'm going to paste it as a values. And let me use this one, Control V, Control C, Control V, Control C, Control V. So now this is my another. Now you can see on iter 3, the MSE is not that much, but it has been decreased, and maybe we are reaching to our, minimum value possible. So that's the beauty of gradient descent. Whenever it reaches to its like a core global minimum value, the changes will become minimum, 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 and then we finally converge into that, the global minimum point. So this is what I want to show you in this small video, how gradient descent work, the batch gradient descent work. And you can see what we are trying to achieve, or what we are trying to achieve is to minimize our value. Gradient descent is working on it. So, yep, thank you so much for being here and watching this. I really appreciate that.